Hi students, you know what do you mean by drop S raised to 4 in organic chemistry? No, right? But organic chemistry expert Karthik Krishnan sir will explain how to remember the whole organic chemistry in one page. Let us see his teaching.
Namaste everyone. One of the most difficult branches of chemistry with the student's perspective is always organic chemistry. That's because the feeling is, yes, two reactions are there, how many reactions do I need to remember? So there are multiple ways in which you can make organic chemistry easy. One is the tried and tested method, which is practice. You have understood the reaction in the class, go back home, practice it, write 5 to 8 times so that it gets registered in your memory. Or the smarter way of doing things is, one of the ways is something that I would teach you here, is trying to create phrases or trying to create anagrams or trying to create sentences with which you can relate to the equation and then remember better. So this was something that I initiated while I was a student and helped me immensely. So let's look at how we can make organic chemistry easy through certain shortcuts. The focus here is to relate the shortcut to the equation, relate the shortcut to the name of the reaction. So how we can do it is what we will see with the next set of slides. The first reaction is the halogen exchange reaction. This is the first name reactions that we will study in the first chapter, haloalkanes, haloarenes. So as the name itself indicates, halogen exchange is a reaction where one halogen is replaced by another halogen. So there are two name reactions under halogen exchange. The first is Finkelstein reaction. Now in Finkelstein reaction, what happens is the halogen that is already present is replaced by iodine. So whatever halogen is already there, that is replaced by iodine. For this we use iodide. The reaction is mentioned here. So the shortcut for remembering this reaction is in the name itself. When you look at Finkelstein, which are the first two letters? First is F, the second is I. So F for Finkelstein, which is the name of the reaction, and I is for sodium iodide, because iodine is what is getting replaced in place of the other halogen, or iodide is getting replaced in place of the other halogen which is there. So this is the reaction here. If I take a chloride, sodium iodide in acetone, the halogen gets replaced by iodine. So you don't need to stress too much to remember what happens in this. The name of the reaction itself tells you that it is exchange of iodine. Since the exchange is with respect to iodine, you need to remember sodium iodide. So that is your first one, Finkelstein. The second reaction under the same category is Schwarz reaction. And in Schwarz, the halogen that is replaced or that is coming in place of the halogen that is existing is fluorine, and the reagent that is used is silver fluoride. The shortcut, remember what we always do, what our mind feels whenever we have lunch, is sleep after lunch. S for Schwarz, AF for silver fluoride. Yeah, that's your second halogen exchange reaction. The third reaction, Sandmeyer reaction, one more very, very important reaction for your entire PU as well as competitive. Sandmeyer reaction comes twice in your entire second PUC syllabus. First, you see it in haloarenes, preparation of chlorobenzene. The second time that you see it is in preparation of phenols. And of course, you come across this reaction in the amines chapter as well. Now, what is Sandmeyer reaction, or how to remember what happens in Sandmeyer reaction? The name of the reaction itself gives you a clue. Now, what is the name here? The first word that I have in Sandmeyer reaction is sand. S, A, N, and then I have D. Now what is the letter that comes before D in the alphabetical series? C. So the shortcut is SANC. Now what is SANC? S for Sandmeyer, which is the name of the reaction. A for aniline, which is my starting compound. The starting compound is aniline. N for sodium nitrite. We use sodium nitrite in the presence of an acid at 0 to 5 degrees Celsius. That is the conditions for the first step to happen. So in the first step, we use aniline, HX and sodium nitrite at 0 to 5 degrees, gives us benzene diazonium chloride, which is also called as BDC. Benzene diazonium, azo means nitrogen, diazo means 2 nitrogens, chloride or the halide, which is BDC. That's what is obtained in the second step. In the last step, C for copper halide. We use copper halide in the last step, giving us halobenzene. So you don't need to fret over the starting compounds if you know the shortcut SANC, and you don't need to spend a lot of time thinking about the shortcut as well, because the shortcut is available in the first word of the reaction itself. SAND, instead of SAND, remember SANC. The other significant reaction for which you have a couple of mechanisms as well that you need to know as per the syllabus is nucleophilic substitution reaction, or SN reaction. There are two mechanisms that you need to remember, SN1 and SN2. Now what is SN1, what is SN2? What are the steps that you need to follow while you write the mechanism? What are the things that you need to write if such a question is asked? And how can this question be asked? This question can be asked in 3 ways. Explain SN1 mechanism with an example, explain SN2 mechanism with an example, or differentiate between SN1 and SN2. So these are the 3 ways in which the question can be asked. However way the question is asked, you need to ensure that you write a minimum of 8 points. Now which are the 8 points that you need to write? You can remember by the shortcut drops. Now drops is the word that you have to remember. Drops, S to the power of 4. If you remember drops, you will know which are the points that you need to write. Now let's go in detail what drops mean. D for definition. The first letter D stands for definition of the nucleophilic substitution. If it is SN1, SN1 stands for nucleophilic substitution unimolecular. If it is SN2, nucleophilic substitution bimolecular. That's your first statement that you need to write. The second point that you need to write, R for rate equation. What is the dependence on the reactants is indicated by the rate equation. How fast the reaction will happen, how slow the reaction will happen is given by rate equation. Now the rate equation is different for SN1 as well as SN2. Now what is the rate equation in the case of SN1? Rate is directly proportional to concentration of alkyl halide only, because SN1 is a 2-step process. First step is formation of a carbocation, second step is attack of the nucleophile. In the case of the first step, it is the slowest step. The formation of carbocation is the slowest step. Therefore, that step is called as the rate determining step, or RDS. In the rate determining step, the rate is only dependent upon one reactant, which is alkyl halide. Hence, this mechanism is also called as SN1, unimolecular, because the rate is only dependent on one molecule of the reactant, which is nothing but the alkyl halide. So you write the rate equation, which is your second point. If it is SN2, rate will be proportional to both concentration of alkyl halide as well as nucleophile, because SN2 follows one step process, and that step itself is the rate determining step. and in that step there are two reactants, alkyl halide as well as the nucleophile. So that is what you need to write in the second, as the second point. The third point, O, for order of reactivity. SN2, SN1, the order of reactivity among alkyl halides is different. In the case of SN1, the order of reactivity is tertiary alkyl halide is more reactive than secondary, more reactive than primary, more reactive than CH3X. Whereas in the case of SN2, it is exactly the reverse. CH3X is more reactive than primary, more reactive than secondary, more reactive than tertiary. So that is what you need to mention in order of reactivity of halides. Then P for products obtained. The products obtained under SN1 and SN2 are different. In SN1, the products obtained is a racemic mixture. If I start with a chiral alkyl halide, if I start with an unsymmetrical alkyl halide in the first step, then in the last step I will get 50% each of the stereoisomer, 50% of the dextro form, 50% of the levo form. Together we call it as a racemic mixture. A racemic mixture is formed in the case of SN1, or in other words, both inverted as well as retained products are seen in the case of SN1. In the case of SN2, there is only one product that is formed. 100% product will be inverted product, and this process of inversion is called as Walden inversion. Yeah, so this you need to write under products obtained. The first of the S is solvents. SN1, SN2 make use of different solvents altogether. In the case of SN1, the solvent that is used is a polar solvent. In the case of SN2, the solvent that is used is a non-polar solvent. Now, why do I need a different solvent in each one of these mechanisms? We know that in the case of SN1, the first step forms the carbocation, and the moment ions are formed, they need to be stabilized. That's the role played by the solvent. Ions will be stabilized in the presence of a polar solvent. Hence, for SN1, I need a polar solvent. Whereas in the case of SN2, we don't have any ions that are formed, so a non-polar solvent is enough to carry out the reaction. So SN1 involves a polar solvent, SN2 involves a non-polar solvent. The second S, steps involved. We spoke about it, but we will just mention it once again. SN1 is a two-step process. First step, formation of a carbocation. Second step, attack of the nucleophile. SN2 is a single step process via a carbocation formation, via a transition state formation. Now, what is a transition state? A transition state is a state where the carbon halogen bond is not completely broken and the carbon nucleophile bond is not completely formed. Hence, we show it as dotted lines there. When we see the mechanism, it would be very clear. Yeah, so these words you need to write under steps. What are the steps involved? The third S, stereochemistry of the products. So we spoke about it when we did the products, but specifically we'll speak about stereochemistry here. If I start with SN2, or if I'm looking at SN2, the product that is obtained is inverted in nature. The configuration will be inverted in comparison to my starting alkyl halide. Whereas in the case of SN1, I will get both inverted products as well as retained products in the ratio of 50-50. Therefore, the mixture that is obtained is a racemic mixture. So we speak about it in stereochemistry. And finally, the last S is the strength of the nucleophile. Now, what should be the strength of the nucleophile in the various mechanisms that we have seen? In the case of SN1, either a weak nucleophile or a strong nucleophile can be used. In other words, any nucleophile can be used, because the halogen is removed already in the first step. In the second step, all that the nucleophile has to do is to go and attack my carbon. Whereas in the case of SN2, I need a strong nucleophile. Why do I need a strong nucleophile there? Because the nucleophile is competing with the halogen that is already there. That's what the transition state is all about. The transition state is a state where the halogen and the nucleophile are fighting against each other. who needs to take that spot. And who will win? The one that is stronger among the two will win. That's the reason why I need to take a stronger nucleophile there. The moment I take a stronger nucleophile, it will overpower the halogen and ask the halogen to leave at the end of the transition state, such that the nucleophile remains. And we have seen the attack. The attack happens backside. It will avoid the halogen that is already there. It will come all around and attacks the carbon from the back. Yeah, this happens because point number one, maybe there is repulsion between both the halogen as well as the nucleophile due to like charges. And two, halogen is big. It does not provide enough space for the nucleophile to come and attack. So to avoid this, the nucleophile comes all the way from behind and attacks the carbon. Yeah, so we have seen this story as well when we looked at the mechanism. So the strength of the nucleophile with respect to SN1, a weak nucleophile is enough to carry out the reaction because the halogen is already removed in the first step. In the case of SN2, the nucleophile that is used should be a strong nucleophile because it has two things to do. One, it has to attack the carbon, and two, it has to drive away the halogen. It can only happen if the nucleophile is stronger than the halogen that is already present. So typically we can create such statements or such phrases or anagrams or words to remember the various steps involved, or to remember the various reagents that are involved in each reaction. This has helped me amazingly, tremendously over the past of so many years. You can create this for literally every subject. This is not chemistry specific. This is applicable to any subject, anywhere where you need to remember certain facts. I hope this has been helpful. Thank you.